Okay, so welcome to this next video in which we are looking at the effect of sympathetic stimulation on the heart. So far we have seen that the noradrenaline is going to act on beta-1 receptors, and it's going to increase the inotropy of the cardiac myocytes, okay? And it's going to do this by leading to the activation of protein kinase A, which is going to phosphorylate the L-type voltage-gated calcium channels and increase their inactivity. It's also going to activate the type 2 ranitidine receptor. Both of these are going to lead to the increased amplitude of the calcium spike here. So it's going to lead to increased release of calcium into the cytoplasm every time an action potential arrives at that cardiomyocyte. Okay, that's going to increase the recruitment of sarcomeres, basically. It's going to increase the number of sarcomeres we recruit every time the cardiomyocyte undergoes an action potential. And if we have more sarcomeres contracting, then we're going to get more force out of that cardiomyocyte, and we're going to eject more blood from the chamber, and therefore have a greater stroke volume, and therefore a greater cardiac output. Okay. In addition, we've seen that protein kinase A of the first type phosphorylates phospholamban, which usually inhibits the SERCA2 pump. And when you phosphorylate phospholamban, it no longer can inhibit the SERCA2 pump. So the SERCA2 pump is going to work more effectively. It's going to return the calcium back into the sarcoplasmic reticulum faster, basically, during the interval phase. So it can cope, basically, with the increased calcium that we release. And that's very, very important, because there would be no point of increasing the size of this calcium spike if the SERCA2 wasn't then capable of getting it all back into the sarcoplasmic reticulum quickly. Because if the calcium were to remain in the cytoplasm of the cell, it keeps some of those sarcomeres in a permanently contracted state. And then basically, you can't make those sarcomeres contract the next time you have a calcium spike, because they're already contracted, so they can't contract anymore, so you can't get any more work out of them. So if you want to get the maximal amount of force generated by a cardiomyocyte, what you need to do is you need to have as many sarcomeres contracting as possible each time you undergo an action potential, and secondly, you need to have them all relaxing during the interval phase. And in order to get them all relaxing, you need to take calcium level back down to 100 nanomolar, and activating the SERCA pump allows you to cope with the increased calcium that you're releasing into the cytoplasm each time. Okay, right, so we've now seen that we've got these bigger calcium spikes, but in fact, protein kinase A does one more thing. It actually goes to the machinery of contraction, the sarcomeres, and increases their sensitivity to calcium in order to try and increase the number of sarcomeres that are recruited upon a calcium spike. So we're going to also increase the sensitivity of the sarcomeres. So let's discuss that now. So within our cardiomyocyte, we have these structures known as sarcomeres. Okay, so let's say this is our cardiomyocyte here. Okay. Within the cardiomyocyte, we have absolutely loads of these sarcomeres, which are the contractile units of muscle, basically. Okay, so let me show you the structure of a sarcomere. So you start off with these two Z discs, as they're called. Okay, and although they look like lines on this 2D slice, what you have to remember is that this cardiomyocyte, which I've drawn as a box, it's actually a cylindrical structure. So basically, I've just sliced down the middle of it, and I'm showing you that slice. But in fact, this is a cylindrical structure. So in addition, these lines, they are circular discs, basically. So let me try and draw that for you here bigger. So I'm zooming in on one of these sarcomeres and drawing the whole structure here now. So these are these Z discs here. So let me color code it for you. So in purple, these are the Z discs, and they're also referred to as the Z lines, because when you look at them down the microscope or down an electron microscope, they look like lines. Okay, so these are Z discs in fact, though. Right, Now, the Z discs have actin filaments attached to them. So here are actin filaments coming this way. Okay, and I will colour these actin filaments in green. Oh, and I want to put them in on this littler picture as well. So here are the actin filaments. Now, I've only drawn 3 of these actin filaments to make the picture as comprehensible as possible, but in actual fact, you'll have absolutely loads of these actin filaments. So these are going to be shown here in green. So to keep the picture nice and easy to understand, though, I've drawn 3 of them. Now, what is the structure of an actin filament? Well, an actin filament is made of the actin protein, but that's not that helpful. So I'll show you actually how you make an actin filament out of the actin protein. So the actin protein is basically a little globular protein. It's a little circle. Okay, so it's a little protein, so it doesn't look anything like a strand. So how do you create these sort of strand-like structures, these filaments, from the actin protein? Well, basically, you polymerize it together. So you join multiple actin monomers together to make an actin polymer, also known as an actin filament. And as you can see, you can continue this on, putting 2 actin proteins side by side and producing a nice long actin filament or an actin polymer or a strand of actin. Okay, and these actin filaments are what you are attaching to these Z discs shown in purple here. Now, in between these 2 Z discs, what you will put is another proteinaceous disc. So here's another disc, known as the M disc or the M line. Again, because when you look at it in 2D like this, it just looks like a line, but its actual structure is a disc, so we should call it the M disc. So this is the M disc. Okay, and let me just colour this in. So we'll have this in orange, I think. So in orange, this is the M line, here's the M disc. Okay, and attached to the M disc, you then have another type of protein filament going both ways. So you have protein filaments going this way and protein filaments going this way. And these protein filaments are filaments known as myosin filaments. So these are myosin filaments. Okay, and I'll colour those in blue. So, in blue here, these are myosin filaments attached to the M disc. And the reason the M disc is called the M disc is because it's got the myosin attached to it. So it's the myosin disc, if you like. Right, so now let me discuss with you the structure of a myosin filament. So a myosin filament is made up of a myosin protein, just like the actin filament is made up of these actin proteins. Okay, so a myosin protein looks like this. It has a fibrous portion, okay, and then it has the head. So this is the myosin head here, and this is the fibrous tail, in fact it's usually called. Right, now what you can do is basically you can put absolutely loads of these myosin proteins together, where you join their fibrous tails together, you coalesce their fibrous tails, and then you let the heads stick out the side. So here are these fibrous tails which we're putting all together to make into a filament, and then sticking out the side you then have the heads off the side like so. And this is then a myosin filament when you connect them all together. So you've got all the fibrous tails stuck together, and then off the side you've got these myosin heads sticking out from the myosin filament, which is made up of the fibrous tails. This is the myosin filament, this entire thing. So this is a myosin filament. And I think this pen's starting to go. No, it doesn't look as though it is. For myosin filament. Okay, right. Now you will notice that the myosin heads are oriented in a certain way. Okay? So at the moment, in this myosin filament, all the heads are kind of pointing in that direction. Now, this is what a myosin filament on this side would look like. Basically, on each of these myosin filaments, the myosin heads will be pointing in the direction of their respective Z disc. So these myosin filaments, they will have their heads pointing in this direction here. And these ones here, they're effectively this, spun 180 degrees around. So these will have all their heads pointing in this direction here, i.e. towards their respective Z disc. Now, what can happen, the way in which you trigger contraction of this cell, and actually before I talk anymore, I want to finish this sarcomere here. And this, by the way, is one sarcomere. From one Z disc to the other, this is a sarcomere. Okay, and this is what's known as the contractile unit of muscle, basically, of skeletal or cardiac muscle. You don't, for some reason, call these equivalent structures sarcomeres in smooth muscle, but they are the equivalent structure. Okay, so here's our sarcomere. Right, and the way you get contraction of the sarcomere is that the myosin heads can gradually sort of pull the actin filaments towards themselves, basically. So these, when you trigger contraction, what will happen is these myosin heads will start pulling these actin filaments here in this direction, and these myosin heads here will start pulling their actin filaments in this direction. So what's going to happen effectively is these two Z lines or Z discs are going to move closer to one another, and that's going to contract the sarcomere. Now, how does this lead to the contraction of the whole cell? Well, effectively what you have is you have whole rows of sarcomeres. So these Z discs, they won't just have actin going one way, they'll have actin going the other way too. Then you'll have another Z disc further along, which will also have more actin here, like so. And in between you'll have another M disc with its myosin filaments here. Okay, so let me colour this one in. So here in green are our actin filaments, to remind you, and here in blue are our myosin filaments. Okay, here in orange is our M disc, and here in pink is our Z disc. So you'll get these whole rows of sarcomeres, and it will continue on this way and this way. And when you finally get to the end of the cell, the final sarcomere will be connected to the membrane of the cell. So basically, when each of these sarcomeres in this row contracts, it will mean that the whole row is going to contract quite a bit, and that will pull on the two sides of the cell and contract the whole cell. And you won't just have one of these rows of sarcomeres, you'll have multiple rows of sarcomeres within your cardiomyocyte. So you're going to have a lot of sarcomeres contracting, which will pull the two ends of the cell together and contract the cardiomyocyte. Right, so how do you trigger the actual beginning of the shortening of these sarcomeres? Well, basically, there is a protein, usually, that is wrapped around the actin filaments and is preventing the myosin filaments from interacting with them. And this protein is known as tropomyosin. Okay, and we'll continue this discussion in the next video.